Welcome to David Alexander Maths Tuition. This is Chapter 7D on mathematical proof. So this is a bit of a slippery topic, but what we need to do is we are proving something using known theorems or facts. We're not just inventing random things, and we're showing some clearly shown logical steps in order to come to a statement of proof. Now these logical steps, obviously these have to be mathematically accurate. No use reinventing the laws of maths to prove something, because then clearly your proof will be completely erroneous. So we're showing clearly shown logical steps, and often this is just doing some algebra, for example, so that we can arrive at a statement of proof. Okay, so here's a statement: the product of an odd and an even number is even. So how do we prove this? So what we could do is let's take an odd number 5 and let's take an even number 4. The product means multiply them together, of course, so 5 times 4 is 20. Oh look, we've got an even number. But that is not proof. That is potentially just one random example where we are multiplying an odd and an even by an even. Okay, but you're probably thinking, well, everyone knows that an odd times an even is an even, but how do we prove this? So first of all, we're going to use some algebra for this one. So an even number we're going to represent as 2n, and an odd number is 2n plus 1. Okay, if n is a number, when you double it, you're always going to get an even number, because anything multiplied by 2 is always an even number. And when we add 1, so here we've got 2n plus 1, so we know that 2n is an even number, so if I add 1 to an even number, I'm going to get an odd number. Now if I expand these brackets, I'm going to get 4n squared plus 2n. Now I can divide through by 2, so that's 2 lots of 2n squared plus n. Okay, so if n is an integer, if I square it and multiply it by 2 and add it to itself, I've got another integer. And then if I multiply that by 2, it must be even. So there we go. So our final concluding statement is, so the product of an odd and even number is even. Now when we're doing proof, we just need to remember, how do we represent, for example, any integer? Any integer, n. An even number, as we've just seen in the previous example, is 2n, because when you multiply any integer by 2, it will be even, and an odd number is an even number plus 1. You could put 2n minus 1. You could put 2n plus 177. As long as you're adding an odd number onto 2n, we've got an odd number. Now for consecutive even numbers, well, if the first one is 2n, then the next one will be 2n plus 2, the one after that will be 2n plus 4. For odd numbers, we know the first one is 2n plus 1, so the next one will be 2n plus 3, 2n plus 5, etc. Now if you've got a question where it says just 2 even, just like 2 random even numbers, not consecutive even numbers, then we'll represent one as 2n and the next one as, well, let's say 2m. I mean, it doesn't have to be the letter m, could be any letter at all, but generally the first one we'd use an n, the next one an m. Similarly for odd numbers, 2 random odd numbers, or one will be 2n plus 1 and the next one will be 2m plus 1. Okay, so prove that the product of 2 odd numbers is odd. So 2 odd numbers, not consecutive odd numbers, so I'm going to use 2n plus 1, and the product means multiply, so I will multiply that by 2m plus 1. So expanding the brackets, I'm going to get 2nm plus 2m plus 2n plus 1. Now, how do I prove that it's odd? Well, this part here is divisible by 2. So that's 2 lots of 4nm plus m plus n plus 1. So we know that this is even because 4 lots of an integer times an integer plus an integer plus an integer will be an integer, and when I multiply that by 2 it will be even, but then when I add 1 to an even, it is odd. So therefore we can say, so the product of 2 odd numbers is odd. Okay, prove that the sum of 2 consecutive odd numbers is always even. So here we're adding 2 consecutive odd numbers, that would be 2n plus 1 plus 2n plus 3, and that is 4n plus 4, and that can be 2 lots of n plus 2. So here we've got an integer. I'm going to add 2 to it, so that would make it either odd or even, depending on whether n was odd or even. But when I double it, it will turn it into an even number. There we go. So we can now make our concluding statement. So the sum of 2 consecutive odd numbers, excuse the handwriting, is always even. Done. Okay, so with these ones, we've got this symbol here, which means is identical to. So all we need to do is just show that this left-hand side is identical to the right-hand side. So all we need to do is expand the brackets, basically. So all I'm going to do is I'm going to write, so it's the left-hand side that I'm playing around with. So the left-hand side is identical to 5x plus 2. I'm going to expand out these brackets. That's x squared minus 4x minus 21. And multiplying through by 5x, that's going to be 5x cubed minus 20x squared minus 5 times 21. Can I do that without a calculator? Yeah, minus 105x. Multiplying through by positive 2 plus 2x squared minus 8x minus 42. So that is identical to 5x cubed. Minus 20 plus 2 is minus 18x squared. Minus 105 minus 8 is minus 113x minus 42. And that we can now say is identical to the right hand side. So therefore I have proved that this stuff on the left is identical to the stuff on the right. Okay, here's a similar example. So it's your choice as to whether you want to play around with the left hand side or the right hand side. I would always be thinking, like, which side can I do the more interesting stuff with? So I mean, on the right hand side I could expand the brackets, but if I expand the brackets there's no way I'm getting this fraction, but I can do something a bit more interesting to the fraction on the left hand side because I've got a surd on the bottom and I can rationalise the denominator. So I'm going to mess around with the left hand side here. So I'm going to say that the left hand side is identical to 3x lots of 2 minus root 5 over 2 plus root 5 to take away root 5, and that is identical to, expanding the bracket, 6x take away 3x root 5 over 4 take away 5 minus 1. So what I can do, I've got this negative denominator, I can turn that into a positive denominator by flipping the sign of everything. So that will become minus 6x plus 3x root 5 over positive 1. I don't need to write positive 1, and if we want we can turn this into 3x root 5 take away 6x, and we can factorise out 3x from both sides. So that's going to be 3x lots of root 5 take away 2, and then we can say that, well, that is identical. We now just say that the left hand side is identical to the right hand side, and we have proven that those two things are identical. Okay, similarly with this example here, what I'm going to do is I'm going to say that the left hand side is the same as y minus 3 over y multiplied by y minus 3 over y multiplied by another y minus 3 over y. So I'm just going to take two of the brackets first of all, so that's going to be y squared minus 3 over y times y. That y will be on top, so that'll be 3y over y, in other words 3. So that's minus 3. I've got another minus 3 on the outside, so minus 6 plus 3y multiplied by 3y, so 9 over y squared. And that will be multiplied by another y take 3 over y. So that is identical to multiplying through by y cubed take away 6y plus 9y over y squared. So that's plus 9 over y. Now multiplying through by the minus 3 over y. So that will give me minus 3y squared over y, so minus 3y. Minus 6 times minus 3 over y will be plus 18 over y. And 9y squared multiplied by 3 over y will become minus 27 over y cubed. Okay, now can I tidy this up a little bit? So I've got 1y cubed. I've got 6y and a 3, well, minus 6 minus 3, so that is minus 9y. I've got plus 9 over y plus 18 over y, which is plus 27 over y. And then I've got the minus 27 over y cubed. Now hopefully we can see that this is pretty much the same as that if I just bring these denominators up. So that is identical to y cubed, take away 9y. So if it's y on the bottom, it's y to the 1 on the bottom, that will turn it into y to the minus 1 on the top. Y cubed on the bottom will become minus y to the minus 3 on the top. There we go, and that is the same as the right hand side, so we can say that the left hand side is identical to the right hand side. Prove that the following points A, B and C are the vertices of a right angled triangle. So for this one we're not going to use any algebra at all. We will be using Pythagoras. When we're talking about right angled triangles, generally speaking, we're thinking about Pythagoras or maybe some trigonometry, but here this has got nothing to do with angles. So what is the length of AB? Well, AB is going to be the square root of 3 squared plus 1 squared, and if you don't know what I'm doing here, then maybe just go back to look at the distance between 2 points. So that is root 10. BC is the square root of 3 squared plus 9 squared, and the square root of 3 squared plus 9 squared is 3 root 10. And let's do AC or CA. AC is going to be the square root of 6 squared plus 8 squared, which is 10. Okay, so is it obvious that A squared plus B squared is C squared? And even if it is, well, hang on a second, what's the A squared, what's the B squared, what's the C squared? Well, the hypotenuse is always the biggest side, so maybe this is, AC is probably the hypotenuse if it is indeed a right angled triangle. So let's try this. Root 10 squared plus 3 root 10 squared equals, well, root 10 squared is 10, 3 root 10 squared is 9 times 10, which is 90, which equals 100. The square root of 100 is 10. Okay, so therefore we've proven that this is a right angled triangle because AB squared plus BC squared equals AC squared. When we are doing proofs, if you're maybe proving that something is a square, just think of basic properties of a square. That is that opposite sides are equal, all the sides are the same length, and the sides are perpendicular to each other. So then if we're thinking about sides being perpendicular, we need to be thinking about gradient of lines. Exactly the same for a rectangle as for a square, except opposite sides are equal, but of course not all 4 sides are the same length. Parallelogram, we need to be showing that opposite sides are the same length and parallel to each other, so again we need to be thinking about gradients here. For a rhombus, exactly the same as the parallelogram, except all the sides are the same length as well. Now for a kite, we would just be showing that these 2 sides are the same length and these 2 sides are the same length. For a trapezium, we just need to be showing that there is 1 pair of parallel sides. So if that's all you can prove, that there's 1 pair of parallel sides, then it must be a trapezium. And for an isosceles right angled triangle, then it was a fairly poor drawing. Then to show this is a right angle, then these 2 sides must be the same length, but crucially to show that this is a right angle, one side would need to be perpendicular to the other. So again, we're looking at gradients. So just remember, if you need to prove the same gradient, then the in the y equals mx plus c. So the m must be the same value for both, and for perpendicular, the m value, well, one must be the negative reciprocal of the other, or alternatively their product is -1. Okay, here's a different style of question, and for this question we're going to use completing the square. So what I'm going to do is I'm going to complete the square and work out the turning point, because the turning point will be the minimum value if it's a positive n squared, or a maximum value if it was a negative n squared. So first of all, to complete the square, I'm going to need to divide through by 5. So that's n squared plus 4/5 n plus 2. So completing the square on the n squared plus 4/5 n is going to be n plus 2 over 5 all squared minus 4 over 25 plus 2. Now just going to, what is 2 minus 4 over 25? Well, that's 46 over 25. So that's going to be 5 lots of, big bracket, little bracket, n plus 2/5 all squared plus 46 over 25. Multiplying through by 5, that's going to be 5 lots of n plus 2/5 squared plus 46 over 5. So the turning point is going to be minus 2 over 5, 46 over 5. So if we think of this as a quadratic, then the x coordinate here is minus 2/5, or maybe it's easier if I just draw an axis as well. Okay, negative 2/5, let's say minus 2/5 is here, minus 2 over 5, and the minimum value is, the minimum y value is 46 over 5, so the graph will look like this. So we can see that there's no x-intercepts, it never goes below the x-axis, so it's always positive. So because the minimum value is 46 over 5, so that might be our proof, our statement here. Minimum value is 46 over 5, so 5n squared plus 4n plus 10 is always positive. There we go. Okay, here's another example. Kx squared plus 6kx plus 7 equals 0, where k is a constant, has no real roots. So here I'm thinking the discriminant because it's talking about roots. So if it has no real roots, then b squared minus 4ac is negative, must be less than 0. So b is 6k, so that is going to be 6k all squared. Take away 4 times by a, which is k, times by c, which is 7, must be less than 0. So 36k squared minus 28k is less than 0. Okay, so I can factorise out, this is divisible by 4 and k, so 4k, and that is 9k minus 7 is less than 0. So if we just think about how we normally solve quadratic inequalities, I'm going to get one solution here which is 0, and another which is positive 7/9. So 7/9 and 0. So where is it less than 0? Well, that is where k is between 0 and 7 over 9. Okay, so we're nearly done, except we've got this funny thing where k is also equal to, it must be greater than, but also equal to 0. So presumably when we put 0 in, we're not getting any roots either. Okay, so if we've got the equation is y equals kx squared plus 6kx plus 7. So if I were to put 0 through the function, then I would be getting y equals 0 times x squared, well that's nothing, plus 6 times 0 times x, which is nothing. So it'd be y equals 0 plus 0 plus 7. So the line is y equals 7. And we know that the line y equals 7 doesn't cut through the x-axis, so also, well, that therefore shows that the line y equals 7 has no roots, and therefore 0 will also satisfy that inequality. Okay, so here's another type of question. Here we're proving an inequality. So all we need to do is prove that all this stuff here is greater than or equal to -8. So it would seem logical, first of all, to add 8 to both sides. So x squared plus 10x plus 28 is greater than or equal to 0. And by completing the square, I can now say that x plus 5 squared minus 25 plus 28 is greater than or equal to 0. So therefore x plus 5 squared plus 3 is always greater than 0. Now at this stage here we can think about what the turning point is, of course, which would be -5, +3, and I suppose if we were to draw a little sketch, -5 plus 3, well, that is always greater than 0. Here's another way we could think of it. We've got something squared, which is always positive, And when I add 3 to that, well, that will still be positive, so it must be greater than or equal to 0. So I could write a statement to that effect. However, we do need to be careful, because just because we finished with what we appear to be a true statement doesn't necessarily mean that we started with a true statement. So what we need to do is just call this our jottings, and let's work this backwards. Now, we cannot dispute that x plus 5 squared plus 3, that is always greater than 0. Okay, that cannot be disputed. So, I mean, it does seem a bit pointless. We're just doing exactly the same thing but backwards. Now, if I expand the brackets, x squared, so that would imply, that's what this arrow means, x squared plus 10x plus 25 plus 3 plus 28 is greater than or equal to 0. We cannot dispute, so we've not done anything mathematically dodgy there. And therefore, that would imply that if all of this is greater than 0, then x squared plus 10x plus 20 must be greater than or equal to negative 8. All we've done is reversed all these equations, but again, it's just to make sure that what we're doing isn't ambiguous, that we haven't, I don't know. So again, like as I said before, just because we finished here with something true doesn't necessarily mean we started with something true. So we have to work it backwards just to check that that is the case. Okay, prove that k squared take away k is always a multiple of 2. So this can be factorised, so that is k lots of k minus 1. So if k is an integer, this is 1 less than k. So what that means is if k is even, k minus 1 is odd. So what we have here is even multiplied by odd is even, or a multiple of 2. Okay, or let's consider it the other way around. If k is odd, then k minus 1 is even. And again, odd times even, or even times odd is even, so therefore it is always a multiple of 2. Prove that k cubed minus k is always a multiple of 6 for all integers where k is greater than 1. So similar to the previous question, not exactly the same of course. So first of all, I'm going to factorise out the k lots of k squared minus 1. Now hopefully you've spotted that this is the difference of two squares, so that can be factorised to k plus 1, k minus 1. So if k is an integer, k plus 1 is 1 more than that integer, and k minus 1 is 1 less than that integer. So I've got a k take 1, putting them in order, you don't have to do this of course, but I've got a k minus 1, I've got a k, and a k plus 1. So 1 less than k, k itself, and 1 more than k, so 3 consecutive integers. Okay, so these are 3 consecutive numbers. So if they are 3 consecutive numbers, then one of them, or at least one of them, so one of k minus 1, k plus 1 must be even, so must be a multiple of 2. And if I've got 3 in a row, we'll pick any 3 numbers in a row, one of them must be a multiple of 3. So one of k minus 1, k plus 1 must be a multiple of 3. So we can say if 1 is a multiple of 3 and another a multiple of 2, k cubed minus k must be a multiple of 3 times 2, which is 6. There we go.